All right, let's start looking at this slideshow as a video that involves the inverse functions. Okay, so let's start with it now. It might take actually two or three presentations to get through it all, but here it is. Okay, so we're talking about inverse functions. Now, let's go back and look at something we already did in the previous slideshow on the previous videos. Okay, we're talking about what happens when we take compositions of functions. Okay, and there is a peculiarity at sometimes when you take the compositions of two functions and they give you the same thing either way. So we're looking at our example, f of x equals x cubed and g of x equals the cube root of x. So let's take the composite fg of x, which of course is again putting all of g in for x. So here it is, color coded to try to help you out. Okay, and we just translating the cube root into the 1/3 power and showing that yields x. Okay, and then here we go again. The composition the other way around, color coded again. The blue function going into the red function as it demonstrates there, and it yielding x. Okay, so there is a peculiar nature about these two functions. As we will see is the same with these two functions, taking their compositions either way. So fg of x, all g going in for x over here, performing the sequence of operations, simplifying, we get x. Likewise, the composition taken over here, in the opposite composition, we also yield x. Okay. And lastly, we take this, which some of you seem to have trouble with, composition of this magnitude. So pay close attention and even execute it for yourself. Fg of x, the composition fg of x, again, all of g being replaced everywhere we see an x over here, minus 5, okay, and likewise in the denominator. We need to tie our terms together going from the left to the right here. So we're going to put them on a common denominator of x minus 1. And we're going to simplify that, and that expression yields x. And you should confirm, validate this, that the composition the other way, the g f of x composition also yields x. But again, you should do that work because a lot of you need practice on that. So do that composition and show that that yields x. So these sets of functions in each case, when composed fg of x or gf of x, gave us the same thing, and in fact all of them collapsed to simply yielding x. So that gives rise to some peculiar nature, and that is of course the peculiar nature of the inverse functions, which we're going to start talking about. So as we saw, given two functions, if we saw that the composition of the functions given either way results in the same thing, and the same thing yielding x, then we're making the claim that those two functions, fg of x and g of x and gf of x, are in fact what we call inverse functions of each other. Okay, so by definition, inverse functions are two functions whose composition fg of x and gf of x yields x either way. Now there's also something geometrically peculiar about these functions, as we'll see as well. So we're going to see that these functions, which are inverses, are exact mirror images of one another across the line y equals x. If g of x is an inverse of f of x, then we'll show its relationship to f in the following notation. So we'll claim that g of x is now f inverse of x. So this is the notation to the -1 after the -1 of x. That is the notation implying the inverse of the function f. So don't get this f -1 of x confused with implying a negative exponent. It does not. So be careful about that, and hopefully within the context of the problem you'll be clear on that. Okay. So let's continue. We have So we saw that these functions were inverses of each other. Now let's kind of graphically depict that for you by graphing them and showing how they relate to one another across the line y equals x, okay? So here's a graph of the cube root of x, which you should all know very well, okay? And here's our line y equals x. And if we were to flip that across the, if we were to flip this this function, the cube root of x, across this line y equals x, okay, then we would look at the x cubed function, which is in fact its inverse. Okay, so that's the geometric relationship with that. And one thing you could take note of just by a point-by-point comparison, you know, if we go on the cube root function, then surely we agree that the cube root function contains 8, 2. Okay, so you know, if you take the cube root of 8, it yields you 2. And the inverse function contains the point 2, 8. Okay, because if you cube 2, you get 8. And that's by no mistake. That's another claim to fame with inverse functions. So as is stated here, if a function contains a point AB, okay, if the function contains the point AB, then its inverse will contain the point BA. I think we're going to stop this video at this stage. What we're going to say is, in summary here, okay, we saw that, okay, a couple things rang true for inverse functions. They are such that when you take the composition either way, it yields x. The notation given to inverse functions is implied here. The geometric representations of inverse functions is that they are reflections of each other across the line y equals x. And for every point AB on the function, its inverse would contain the point BA. Merely the x and y values coordinates are flipped because the function is flipped across the line y equals x. So again, the rationale behind a function containing AB and its inverse containing BA is because inverse functions are simply reflections of each other across the line y equals x, where y becomes x and x becomes y. So as I said, I think we'll end this presentation here and pick up with a new one momentarily.